This is the second example that we'll be discussing on this board. So in the text 3.9, now it's actually a return to M1. Now remember we used this Turing machine to introduce what a Turing machine was via one concrete example, and it was this one. But we didn't go into details. We did not give all the transition rules. We just gave a sort of higher level overview of what the strategy was. And if you remember, if you're a bit fuzzy, go back to a board or two back and revise. I can maybe refresh your memory a little bit. Yeah. So you have the language now is of this form. You have an arbitrary binary string here, set 01 starred. This is just an arbitrary binary string of any length, right, starred. And your language consists of that arbitrary string, hash, the symbol hash, followed by a clone, the same, identical same string W on the right hand side of the hash. So the binary strings either side of the hash have to be the same. So any string satisfying that property, that form, belongs to this language B. And your task is to create a decider, meaning a Turing machine that decides that language. In other words, all strings of this form will be accepted by that Turing machine, and all strings not of that form, not of this form, will be rejected by the Turing machine. In other words, the Turing machine decides all strings. Okay. Right. So let's do a quasi-formal description of this Turing machine. Now we won't. Now you can see it's already fairly complicated. It's more complicated than the previous one. And that's the reason why it's our second example. And in fact, the number of states written down here is 7. But if you look in here in the formal description, your seven tuple for the Turing machine, your Q here, capital Q is by definition, quite used to this, the set of the states of that machine. Sipser has listed, besides the two halting states, and by the way, again, that's QA is me, I'm saying that. It's just shorter to write than Q accept, and QR similarly. So except for the two halting states, he's got 14 ordinary states mentioned. And here there are only 7. Wait a minute. No, it's not true. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what happened to the other 7? 7. So is this correct? I mean, he does mention, you'll see later on, to simplify things, there have been states left out. So I have a bit of a question mark. Is that 14 actually correct or not? So I mean, you can imagine, maybe in his first design he decided in his head that he'd do it with 14 states, and he wrote down 14. And then later he changed his mind and then found a simpler way to do things. If you imagine yourself writing the text, right? And then you came across this simpler way of doing things, perhaps, and perhaps, I don't know, forgot to go back and change the number of ordinary states, in a sense, to 14. Now, maybe it is correct. Maybe I don't know. I haven't gone into that level of detail. You can check that out for yourselves if you want. As I say, the general theme of this board and the next is there are a lot of details in Turing machines. Right, so so the grand strategy. So let the join between the marker pen and an ordinary ballpoint pen, let your hash symbol be here, right in the middle, here, the hash. And you're trying to show that from your perspective, this is your left, your right, that the string here, W, is the same as the string here on the right hand side. That these two strings, either side of the hash in the middle here, are the same. And the broad strategy to do that was, if you remember, if not, go back. You look at the first symbol here on your left string, you scan across until you hit the hash, so you know you've finished reading your left string, and then you look at the first symbol of the right string. And if they're equal, if they're the same, if they're both ones or both zeros, that's okay. Then you go back. Oh, the first this first symbol, you overwrite it with an X. Is that right? Or a 0? You see, details. What happens? Let's see. Well, we can probably deduce it from here. Okay, so the start state, we start in Q1. You read a 1, you replace it with X. Okay, if you read a 0, you replace it with X. Okay. That's for later. Okay, so yeah, see, in real time. Okay, so you start here. And you overwrite it with an X, the 0 or 1. If it was a 0, I suppose you go into one state, and if it's a 1, you go to another state. Does that make sense? If it's a 0, you go to Q2. If it's a 1, you go to Q3. Okay. So all right. So you put an X here. You just move across, doing nothing. Just move until you get to your hash in the middle. Then you look at the first symbol here, and if you're in Q2, that means you saw a 0 here. Is that right? Yes, you're in state 2. You saw to get to Q2, you had to see a 0, right? And if it's a 0, that's fine. Then you just scan back. You go back to here. Until you hit your X, and then you look at the next one to the left of that. Now let's see. So if that's a 0 and this is a 1, it should reject. Let's see if this state diagram actually does that for us. Okay, so if this is a 1, so you'll be in state, as you move across, you'll be in state what? I don't know if it's a 1, so you'll be in state Q3. And then you're in Q3 and you see a 0 here, you should reject, right, because they're different. So you're in state Q3 and you're looking at a 0 here. So Q3 and looking at a 0. Q3 looking at a 0. What's that? Doesn't reject. That's odd. Oh! You got to go through. You got to go through all the hash and everything. Sorry. Details. Okay. So how do you reject? Oh. Okay. Another comment. He makes the point here that. I can just read it out actually. Where is it? Okay, so to simplify the figure, and it's already quite complex, the reject state is not shown. Okay, so there's no QR here. There's a QA, but there's no QR, and that was done to simplify the diagram. Okay, so it's already quite cluttered. Okay, and no transitions going to the reject state. So that's what I was looking for. And they're not there, and they're not there to simplify things. Okay, so when the corresponding transition arrow is not there, that implies implicit. There's a reject. You go to the reject state, right? That's what it's saying here. For example, here's an example. So state Q5. There's no outgoing arrow. There's no transition arrow going from Q5 when you read a hash symbol. Well, let's have a look. So Q5 reading hash. Q5 reading hash. Well, there's no mention of it. There's a mention of reading X. There's a mention of reading 1, but there's no mention of reading hash. Just rejects. Okay. If you're reading a hash in state 5, you would reject, and then you need to say, well, why? So for that you need the overall strategy. Now I won't go into details too much with this one. You need to go back to the previous discussion of the functioning of this particular machine, what the task is. You need to go into the actual real details. Remember, the task is you check this one and see it's the same as that one. So you scan across, and then you've marked that one X, you've marked that one X. If they're the same, if they're not, reject. Okay, so you go back, and then you look at the second one and look at is it a 1 or a 0, and you cross it out, and you remember whether it's a 1 or a 0. In other words, you use the state, Q2 or Q3. You use the state to remember whether it was a 1 or a 0, and then you move across. You've hit the hash. And then you as you move through, you have more and more X's. So you just scan, you just move through all the X's until you get your first non-X, and then you look at it. And is it the same as the one you're looking at here? So progressively, you're ping-ponging back and forth, commuting back and forth, and each time you're crossing out the corresponding symbols, putting an X there.